Hi, I'm Stavros Tsaklas. In this lab, we will be analyzing the absorbance of 4 different cyanine-containing dyes. In this lab, we use electronic absorption spectroscopy to characterize the difference in 4 cyanine-containing dyes with differing lengths and conjugated chains. An absorption spectrum is obtained for these 4 dyes, and the wavelength of maximum absorption is used as the key determinant of the energy difference between ground state and excited state. As a mode of comparison, particle-in-a-box methods, Huckel molecular theory, and molecular modeling through Sigris are used. The efficacy of these methods will be analyzed. Now, why does this matter? Each of the 4 dyes contain 2 cyanine groups separated by a conjugated chain. And because these chains are differing in length, each molecule contains a different number of delocalized pi electrons. These pi electrons are what determine the energy gap between the HOMO and LUMO states. So what is the hypothesis? This first equation is what characterizes the quantum mechanical energy for a one-dimensional box. Holding all else constant, as the value of L increases the length of the theoretical box, the magnitude of the energy will start to decrease. Based off the equation where the change in energy is equal to hc over lambda, as the wavelength increases, the change in energy will begin to decrease, signaling that smaller molecules are expected to be absorbed at smaller wavelengths. The key equation for the one-dimensional box model is pictured. This is the expression for the quantum mechanical energy levels of an electron within the system, where n is the principal quantum number, h is Planck's constant, m is the mass of an electron, and L is the length of the theoretical box. In this lab, L is taken as the length between the 2 nitrogen atoms plus 1 bond beyond each nitrogen. The second mode of analysis used is the Huckel determinant. This determinant helps us characterize how pi electrons bond in our conjugated system. Through analysis of the determinant, the resonance integral beta can be solved for. If we divide each term in the determinant by beta, we're able to use the substitution where x equals alpha minus e over beta, giving us a determinant filled with ones, x's, and zeros. The determinant yields a polynomial that gives values for the energy at each level. By finding up to which orbital the pi electrons fill, the difference in energy between the ground level and excited level is obtained. In this experiment, we used an Ocean Optics 4000 CCD spectrometer. 2 biconvex lenses and 2 mirrors were used to redirect the path of our light. 2 bulbs, an incandescent bulb, along with an ultraviolet LED were stacked on top of each other. Once emitted, the light is redirected and passed through a cuvette containing our dye solutions. The light is eventually directed back into the spectrometer. This yields an absorption spectra for each dye. This absorbance graph shows the first results obtained. Each peak is labeled with the wavelength of max absorbance within the visible region of the spectrum. The size of each molecule increases with each peak, with the smallest molecule on the left and the largest molecule on the right. These are the results of the particle-in-a-box model. Molecule 1 being the dye with the smallest conjugate chain, and molecule 4 being the dye with the largest conjugate chain. The number of pi electrons increases with longer conjugate chains. Molecule 1, being the smallest molecule, had the largest value for the change in energy between the HOMO and LUMO state, and molecule 4 had the smallest value for the change in energy. The wavelength at each max absorbance is seen to increase with increasing length of the conjugate chain. The Huckel determinant was solved using Mathematica. This is pictured in the upper left-hand corner. 4 determinants were used, each characterizing one of the dyes. The determinants increased in size with a 5x5, 7x7, 9x9, and 11x11 determinant, with the largest determinant matching the largest molecule. The X values obtained by Mathematica were recorded into Excel, and a plot was generated comparing the delta E values experimentally obtained and the values for the change in the coefficient. Based off the equation that the change in the experimental E is equal to beta times the change in the coefficient, the slope of the line on the graph is equal to beta and had a value of negative 2.6 electron volts. The error of the slope was determined to be 0.135. The last form of analysis used was Sigris. Each of the 4 cyanine molecules was modeled, and a simulation of the absorbance spectra was generated using 4 different models. An example of one of these models is pictured on the right. This is the data collected for the 4 models used. Pictured in the charts is a comparison of the wavelength found from the model compared to the wavelength found experimentally. The last column, labeled closest, indicates if the model yielded the most similar value to our experimentally determined value. It was found that the AM1 MOS model was best for the smallest molecule, and the PM3 MOS model was best for the largest molecule. The RM1 MOS model performed best overall. So what was the purpose of this experiment? This experiment helped us identify how the size of a conjugated chain would relate to the electronic absorption energy of the molecule. As the conjugated chain size increased, the absorption energy decreased, confirming the initial hypothesis. This lab also helped us understand the efficacy of particle-in-a-box and Huckel methods. The particle-in-a-box method was found to not be very accurate in its computation, but was an effective way to demonstrate the trends between the conjugated systems. The Huckel method was very effective at generating a value for the resonance integral with relatively low error. The drawbacks of this lab would be mostly attributed to the precision of the analytical equipment used. Our setup using optical lenses was done by hand, and for that leaves room for error. This lab was better used for characterization of the dye molecules rather than precise computation. This lab could be replicated and beneficially used to characterize other optical related properties of molecules containing conjugated chains. An alternative method could have been to use a standard plug-in-the-cuvette spectrometer. This would negate the need to set up the optical aspects by hand. In turn, this may yield more precise results.